We've talked about the linear function. We've talked about the quadratic function. So I guess the next one up would be the cubic function. Now, there are two basic shapes for a cubic. I guess the classic one, the one we're used to seeing, is this sort of shape. It inflects at the origin for y equals x cubed. But any cubic, that could be factorised down to a perfect cube. So x minus a to the power of 3, maybe times some constant, will have that particular shape. Okay? So the point here at the origin is what's called a horizontal point of inflection. So the curve inflects rather than reflects. So the parabola, for instance, reflects at the origin, as opposed to the cubic inflects at the origin. The other basic shape is this up and down shape. So it's got two turning points. So that'll be the alternative shape if it's not a perfect cube. But once again, just like the linear function, just like the quadratic function, we can create the shape by translating, rotating, reflecting either of the basic shapes. We can get all of the different cubics. And how would we recognise it? Well, much like the quadratic, we're looking for the highest power being 2. Now we're looking for the highest power to be 3. And that tells us it's a cubic. So, all right, polynomials in general. Okay. So obviously there's lots of different shapes polynomials could take depending on what the highest power is and things like that. Now, if it can be factorised down to be a perfect whatever the power is, then it will have a common basic shape. All even powers have this sort of U shape. Now, only x squared is called a parabola. Okay. The other U shapes, because what happens is, as this power gets bigger, it gets flatter at the base and steeper at the sides. The reason for that is, any number smaller than 1 raised to a bigger and bigger power will get smaller and smaller and smaller. So it's getting closer and closer to the x-axis. But once you go past the y value of 1, when you raise it to a bigger and bigger power, then the number gets bigger and bigger and bigger, so it becomes a lot steeper at the side. So that's why the shape changes like it does. Similar thing happens with the odd ones. It has that inflecting shape. I might have exaggerated the flatness around the origin there. That's a very flat graph there. But again, it would get flatter at the base and steeper at the sides as that power goes up. So how do you recognise a polynomial? And we'll investigate polynomials in a lot more detail later. But basically, you've got your algebraic expression, and all of the powers have to be positive integers. So you can't have fractional powers, you can't have negative indices. Okay, so as long as they're all positive integers, then we know we've got some type of polynomial. A polynomial, okay, so we've got names for quadratic and cubic and quartic, but after a while it gets a bit hard, and so we just tend to say, oh, it's of degree whatever the highest power is. So a quadratic would be a polynomial of degree 2, cubic polynomial of degree 3, and so on. So how do we sketch polynomials? So things to look for, same as all the other ones. The y-intercept is the constant value. In this particular one, look, I don't have to expand the whole thing out. If I want to work out the constant will always be the constant times the constant times the constant. So we've got 1 times -1, but it's cubed, still -1, but times 2 squared. So we end up with, what's all that, -4, I think that works out to be, doesn't it? So we'll plot -4, we know the y-intercept. The x-intercepts then would be the roots, the solutions to the equation. Fortunately, this one's already factorised for me, so that saves a bit of time. I know I'm going to have x-intercepts at -1, then the next one would be +1, and the next one would give me -2. So we know those features. Now, where do we start and finish? A polynomial will always act like the leading term out at the extremities. That's an idea of dominance. Because if the number's really big, so we're talking close to infinity, it's huge, then the biggest power is so much bigger than the next one that the others may as well be 0. You think, that doesn't make sense. But it does. Let's even think of a number as small as 100. And so we're saying the biggest power was 7. I mean, 100 to the power of 7 compared to 100 to the power of 6. 100 to the power of 7 is a lot bigger. No, that's just 100. So obviously out of infinity, the difference between the two is huge. So we only have to look at the leading term. Whatever it does, this will do. So our one, the leading term, we're going to have x times x cubed times x squared. So we've ended up with x to the power of 6. Now if I'd said to you, okay, draw x to the power of 6, you know, I'd draw a U shape. So that means this polynomial will start up here, just like x to the power of 6 would, and it will finish up there, just like x to the power of 6 would. So we now know where it's going to start and where it's going to finish. Now the actual x-intercepts themselves, they behave like the factor. So if it's to an even power, then it will have that U shape like an even power would. And the higher the power, the flatter at the base, the steeper at the sides. So we've got an even power there at -2. Now I know it starts up here. So if it's going to be a U shape, then I must turn at -2. I must just come down and touch at that point. Odd ones will also have that inflecting shape. Other than the power of 1, of course, that'll cut through like a straight line. So we've got an odd one over there at +1. Now we know it finishes up here, so it must inflect like that. All right, I know where it starts, I know where it finishes, I know its y-intercept. We can pretty much complete the graph. Now those turning points, and okay, I used a graphing package, so it is quite accurate. Once we know a bit more about calculus, we can locate those turning points exactly. But for a rough sketch, it's not that big a deal. The main thing we're interested in now at this stage is the shape, where it cuts the x-axis, that sort of thing. All right, so next interesting shape then, it's not a function, it's just a relation, our circles. And the most basic circle is the one centered at the origin. And you may recall we get x squared plus y squared is the radius squared. It's really important with this one that the scale's the same on both the x and the y axes. Otherwise it will look like an ellipse rather than a circle. But as I say, they're not actually functions. They're composed of two functions. The top semicircle and the bottom semicircle. They would be functions. So how do you recognise it? Okay. So there's our formula, but the key thing we're looking for, both pronumerals are to the power of 2, but the other key thing is that the coefficient's the same. Now we normally see the coefficient 1, but if we had 2x squared plus 2y squared, that would still be a circle. 3y squared, 3x squared, still a circle. Yeah. So the coefficients have to be the same. If they were different, so I had 1x squared and 2y squared, I wouldn't get a circle. I'd get an ellipse. And if the signs were different, we actually get a hyperbola. But a hyperbola, I think we talked about that the other day, the hyperbola that's been rotated so that the vertex is on the x-axis. Okay. So that brings up functions that have square roots then. There is that top half of the circle. We just said the circle's made up of two functions. There's one of the functions. It's when we have to rearrange the formula usually. See, x squared plus y squared equals the radius squared doesn't have that dependent variable or independent variable for that matter, the subject of the function. So, top half of the parabola would also be an example of that. So recognising the shape, look, if you're not sure, say you got y equals square x and we didn't know it was the top half of the parabola, then just square both sides. When you square both sides, you'll see what the shape's going to be. So our circle up there, well hang on, y equals the square root of r squared minus x squared. Perhaps we didn't recognise that to be a semicircle. Gee, what is it? Square it, rearrange it, and you say, oh, it's a circle. But it's only half of it, so it's the top half of the circle. Similar with the parabola. If I squared, I go, oh look, y squared equals x. I know I have a parabola, but just the top half of the parabola. So if you're not sure, square it. Get rid of the thing that's causing the problem. The root's what's causing the problem. Get rid of it. Square, see if you then recognise the shape. So positive square root will be the top half, negative square root will be the bottom half. Okay, well that'll do us for today. We haven't got some good, so.